Sound synthesis allows us to create sound electronically, whether replicating the timbre of real instruments or generating entirely new otherworldly sounds by manipulating fundamental waveforms. Previously, we used Python to generate and combine simple waveforms, crafting interesting tones from scratch, but real-world sounds tend to change dynamically. So, how can we create sounds that evolve over time? An ADSR envelope is a fundamental concept in sound synthesis. It represents 4 key stages of a sound's amplitude: attack, decay, sustain, release. By adjusting these stages, we can create sounds that feel more expressive and lifelike. Attack is the time it takes for the sound to rise from silence to its peak amplitude. A short attack creates an immediate onset, while a longer attack results in a gradual build-up. Decay is the time it takes for the sound to decrease from its peak amplitude down to the sustain level. Unlike the other stages, sustain is defined as an amplitude level and not a time duration. The sound remains at this level for as long as the note is held. In the case of computer-generated sound, the phrase is determined by the sound's entire duration minus the durations of the other stages. Release is the time it takes for the sound to fade from its sustain level to silence. A short release results in an abrupt cutoff, while a longer release creates a more gradual fade out. Different instruments have unique ADSR envelopes, which contribute to their distinct sound characteristics. A piano, for example, reaches its peak amplitude almost immediately after a key is struck, and then quickly reduces in volume, resulting in a fast attack and short decay. It has a moderate sustain as the key is held, but once lifted, the sound fades rapidly, meaning it has a short release. A bowed violin, on the other hand, has a slow attack since the sound builds up gradually as the bow starts to move across the string. The volume reduces slightly after reaching its peak, resulting in a short decay followed by a long sustain as the bow remains in contact with the string. When the bow is lifted, the sound fades gently, leading to a long release. Let's try to encode this with Python. I recommend you watch my previous introduction to sound synthesis to learn how digital audio works and how to generate a sine tone. Today we'll build on our previous sound synthesis file and write a new function that can apply an ADSR envelope to a waveform. Be sure to have imported numpy as np and sound device as sd at the top of the script. We'll name our function applyEnvelope. Its first argument will be the sound we wish to modify, represented as a numpy array. Its second argument will be the ADSR values provided as a list of float values. The attack, decay, and release times will be specified in seconds, while the sustain level is defined as a ratio of the amplitude rather than an absolute value. If the user wants to adjust the amplitude argument, sustain will scale accordingly. Its third argument will define the sample rate, defaulting to the common standard of 44,100 samples per second. Our function will return a numpy array representing the original sound with the envelope applied. Inside the function, we'll create a copy of the original sound using numpy's copy method. Rather than modifying the original array, we'll apply the envelope to this copy. Returning a new array provides control and flexibility, since the user can choose to keep the original as well as the modified version. Next, we'll need to calculate how many samples are needed for each stage of the envelope. For the attack, decay, and release stages, we can do this by multiplying their duration specified by the ADSR argument by the sample rate. For the sustain samples, we can subtract the total number of attack, decay, and release samples from the overall number of samples. This ensures that the sustain phase takes up the remaining duration of the sound. We can now apply each stage of the envelope to our sound. First, the attack phase. We'll gradually scale the volume of each sample from 0, representing silence, to 1, representing the peak amplitude. Since attack sample stores the number of samples in the phase, we'll modify the portion of the array from the beginning of sound up to attack samples. To do this, we'll use np.linespace to generate a sequence of evenly spaced values from 0 to 1 over the number of attack samples. Multiplying our slice by this sequence smoothly increases the amplitude. To apply the decay phase, we'll modify the portion of our sound that spans from attack samples up to attack samples plus decay samples. This marks the transition from the peak amplitude down to the sustain level. Once again, we'll use np.linespace, this time generating a sequence of evenly spaced values from 1 to the sustain level, stored at index 2 of the ADSR argument, over the number of decay samples. Multiplying our slice by this sequence smoothly reduces the amplitude. To access the sustain samples, we need a slice of sound starting at attack samples plus decay samples and ending at attack samples plus decay samples plus sustain samples. We'll scale this portion by multiplying it by the sustain level, which is stored at index 2 of the ADSR argument. Finally, we'll apply the release phase. To do this, we'll first calculate the starting index of the release phase by adding together the number of attack, decay, and sustain samples. We'll create a slice from that index to the end of the sound array. We'll once again use np.linespace, but this time we'll generate a sequence from the sustain level, index 2 of ADSR, to 0 over the number of release samples. This will smoothly fade the sound out. We can now return the scaled array. In main, we'll use the sine tone function we created to generate a new tone with a frequency of 300 Hz and a duration of 2 seconds. We'll pass this to our apply envelope function to create an ADSR envelope with an attack of 0.5 seconds, a decay of 0.2 seconds, a sustain level of 0.6, and a release time of 0.5 seconds. We'll use the sound device library's play function, and then we'll call sd.wait to ensure the sound finishes playing before the program ends. We can now run the program to hear how our sound evolves over time, shaped by the envelope we've applied. We can tailor the ADSR values to mimic different types of sound. For a plucked sound, for example, we can specify a sharp initial attack, a quick decay, with little sustain and a short release. Ambient pad or synth sounds evolve slowly over time, with a smooth attack and release and long sustain. Percussive sounds can be created with an immediate attack, a short decay, no sustain, and a quick release. Brass instruments tend to have a moderate attack, medium sustain, and a fairly long release. Bell sounds and chimes have a sharp attack, a slow decay, and a long release. Previously, we saw how we could sum sine waves to create more interesting sounds. We can now additionally apply unique ADSR envelopes to each sine wave before summing them. We can experiment further with different ways of layering waveforms by adjusting envelopes to synthesize unique and complex sounds. Let me know your own ideas, and if you'd like to see more videos on sound synthesis with Python. If you found this helpful, please like and subscribe. Leave your questions, feedback, and suggestions in the comments below, and thank you for watching.